X is defined as whatever you see that, log of something another, plus something else divided by something else. And then we have minus k times 1 plus r to the minus t, and another adjustment factor, the normal density function, in order so that we can change the word from being deterministic to being stochastic. Again, I cannot go into how this was derived here, but the idea that I want to get across is that the Black-Scholes formula is no big deal if you look at it from the context of a deterministic world adjusted for probabilistic outcomes. Again, if you go into the handout, you can think of the Black-Scholes model in that sense as if it is the discounted net present value of a lottery ticket, if you will. And you can think of the pricing of an option with that framework in mind. And similarly, for a put option, what is the put formula in a deterministic world?
K times 1 plus r to the minus t minus s.
Minus s. And the Black-Scholes value for a put option would be on page 6. And there again, you will see that it is very similar. The formula is very similar to this deterministic formula, but there are adjustments here and here to account for the world being probabilistic or stochastic. So if you look again at the Black-Scholes formula in that context, the mystique goes out. By the way, it's appropriate for me to talk about, if you derive, are there any questions here? Okay. If you derive the call option price for a European option, you can easily derive the put option price even without using the Black-Scholes formula. And that is what is called the option parity theorem. The option parity theorem. And that says that buying a call and selling a put equals being long forward, being long the instrument in the forward market. Okay. Buying a call and selling a put is equivalent to being long the security in the forward market for European options. Okay. Now let us say why that is the case. Suppose you buy a call option on IBM, shall we say, for $100. And similarly, suppose that you sell a put option on IBM at $100, 3 months out, okay, with a maturity of 3 months. So come 3 months, IBM stock is above $100. What will you do? You will exercise the call and you will buy the IBM stock at $100, right? Now, again, come 3 months out and IBM stock is less than $100 and you've sold a put at $100. What will happen? Right. You have sold a put option on IBM stock 3 months out at $100. Come 3 months, and IBM stock is at $95. What will happen? The person that you've sold the put to will put back that stock to you at $100, right? So therefore, buying a call and selling a put is equivalent to being long that stock, because no matter what happens, you will end up buying that stock at $100 if you have bought a call and sold a put at the same strike price. That leads to the option parity theorem, which states that buying a call and selling a put, that is your cash flow today. You carry that into the future, and in the future you pay an exercise price of X, and that is equivalent to being long the forward contract. That is your riskless hedge. This is the so-called option parity theorem that traders use all the time to arbitrage between the options markets and the forward market. And this also tells us that given that you know the forward price, you can know, and either the call or the put price, you can solve what the other price is. Okay? So therefore, once you know what the call price is in the Black-Scholes formula, through mathematical juggling, you can find what the put price will be. Now let's see how put prices behave as the underlying inputs change. What happens to the put price as the underlying stock price goes up? It goes down, right? Is that obvious to everybody? Does that need any further explanation? As S goes up, this is minus, this has to come down. And the put behaves differently than the call, right? Okay. What happens to the put price as the exercise price goes up, as K goes up? The put price, as K goes up, what happens to the put price? It goes up. As K goes up, the lower the stock, the higher the K, the more you get paid at time to maturity, and therefore the put price should go up. What happens to the put price as time to maturity goes up? What happens to the put price as time to maturity goes up? Okay, now the answer here, the theoretically correct answer here, cannot be gotten simply from the deterministic formulation. Okay? You have to be careful here. The deterministic formulation argues that as the time to maturity goes up, what happens to the put price? Okay, the deterministic formulation argues that as time to maturity goes up, the put price goes down. And what is the intuition behind that?
You have S growing in 1 plus R.
Yeah, but then we discount S as well. So let's forget about S. But let's look at the exercise price, what you would get. You get the exercise price at maturity. As time to maturity grows up, the net present value of that exercise price goes down, right? The net present value of what you get from putting the stock goes down, correct? So as time to maturity goes up, the deterministic formulation argues that the put price goes down.
I'm saying the reason is because you're assuming that everything's growing at the risk of greater interest.
Correct.
Your differential is narrowing, let's say, some money.
That's correct. That's correct. And if you look at this, the present value of the exercise price that you would get as time to maturity increases goes down, right? But that is the factor that the deterministic formulation would argue. But we know that options are like, in a way, like lottery tickets, if you will. That's one way to look at them. And as time to maturity increases, in a stochastic sense, the likelihood that your option will end in the money increases as well. So that should argue that the put should increase in value, right? The longer the time to maturity, the wider the band for the DM dollar rate. or the wider the band for Chase's stock or IBM stock or whatever. And therefore, the higher the likelihood that your option, whether it's a call or a put, will end in the money. So the stochastic world argues that the higher the time to maturity, the more should be your put price. On the other hand, this net present value of the strike price that you receive argues the other way. Ergo, the net effect is ambiguous. And if you take the derivatives of the stochastic formulation, that's what you'll find out. But I wanted to motivate that intuitively. Anything else left? Any other variable left that we didn't discuss? Well, volatility. Again, as with calls, as volatility goes up, the price of the put also goes up. Again, you cannot get that directly from the deterministic formulation. To sum up, the deterministic formulation will tell us the direction of everything except for what volatility does to these prices and except for what happens to a put when time to maturity increases. For these, we have to use our judgment a little bit. For everything else, we can look at the deterministic formulations. First, let's go back to the original model. Remember, an option is equivalent to being long the stock and borrowing money. Okay? So, you have a stock. You have quantity of S of stock. Quantity sub S of stock that you buy now. And by borrowing money, you form this portfolio of stock, quantity sub S, at price S. That's the value of your stock. And you've borrowed money, B. Again, let me rewrite that again. This is the current value of this portfolio. You've bought Q sub S shares of stock at price S now, and you've borrowed money B now. Now let's see what happens. Now assume that the world can take only two possible shapes next period, that we have this period and we have next period. And the stock price can go either up or down. But if it goes up or down, it will go up or down by a discrete amount. It will be in either of two states. So the stock will be either what it currently is S times U, it's the up factor, or S times D. So our portfolio next period will be Q sub S times S sub U plus 1 plus R into B, right? If we are in the up state of the world. And Q sub S times S sub T plus 1 plus R to the B if we are in the down state of the world. And if we are in the up state of the world, the value of the call would be C sub U. And if we are in the down state of the world, the value of the call will be C sub D. Okay. Now, we have two equations here. We subtract one from the, we subtract this equation from that equation. And what we have is Q sub S into S sub U, SU minus SD. These cancel out. We have CU minus CD. And therefore, we have Q sub S equals CU minus CD over SU minus SD. So this says that, go ahead.
In the top part, you're talking about the value of the portfolio?
Right.
So would that be quantity times stock minus the borrowing?
Well, it turns out that B will be a negative number.
Okay, B's negative. Okay.
Okay. When you solve for B, it will be negative.
Okay,
Okay, but it doesn't matter here whether
anyway, but I was just curious.
you can solve it. And it will turn out to be a negative number because that's borrowing. You're short the bond. Okay? But we put it as B when we algebraically do it that way. If it is plus, that means we're long the bonds, and if it's minus, we're short the bonds, which means borrowing. Okay? So that means, well, this argues, this is the essence of delta hedging. This says that if we are in a world that can either go up or down, By choosing Q sub S equal to this, by choosing Q sub S equals to this, we have replicated the call option with another portfolio that consists of borrowing, and the stock. And here is the quantity of the stock that we have to buy. Let me start this way. To price American options, again, we start at time S at time 0 like this, and we assume that the stock splits into two. Okay, it either goes up or down at the first split level. And then we assume that at the second split level that again it goes up or down. And then from here it either goes up, these merge, or down. And again it goes up or down, up